Okay, so let's talk about the topic rationalizing denominators. One thing that I mentioned in the previous video about simplest radical form is that we're not allowed to have any radicals in denominators. So far we've seen a couple of examples whereby either just working out a perfect square of a square for a square root, or by dividing we've been able to take care of them. But here are two examples where that's not going to be possible. And so what we need to do is we need to introduce a couple of different methods to clear this up. Now we call this rationalizing denominators because non-perfect square roots are irrational numbers, and we want to make them rational. Discussion about why we would do this or how we would do this will be something we'll talk about in class, but we can talk about the two techniques that we'll primarily use here. The first technique is for the first example, which is the most basic example, just when you have a square root in your denominator. What we're going to do is we're going to multiply this expression by a really fancy looking 1, because multiplying it by 1 won't change its value. It'll just change the way that it looks. Well, the 1 that we want to multiply it by is going to be another fraction, and we're going to take the denominator and multiply that by the square root of 5 for a reason we'll see in a second. My numerator, in order to make this 1, has to be exactly the same. So that's going to be, we're multiplying by the square root of 5 over the square root of 5. Now I can just multiply, and 1 times the square root of 5 is the square root of 5. I know that. And then the square root of 5 times the square root of 5, well, something that I had mentioned before is that you can multiply the two numbers inside the radicands, or inside the radicals, multiply the two radicands to end up with a new radical. So this is the square root of 5 times 5, which is the square root of 25. And that actually is now reducible. So that leaves me with the square root of 5 over 5, which is actually going to be my final answer. You cannot cancel those two 5s because one is in a radical and one is not. But if you look in a calculator and you do 1 over the square root of 5, either as a fraction or through division, you'd end up getting the exact same decimal that you'd get from the square root of 5 over the square root of 5. And that's the first basic technique. You can see the second one's going to be a little bit more complicated. The problem with this example is I can't just multiply by the square root of 3 over the square root of 3, because although that would clear up the square root of 3 problem in my denominator, I'd also be distributing it to the 1, which would still leave another radical down there. So I actually have to employ a difference of squares, which is something I haven't done since our factoring chapter. So what I'm going to do is I'm going to multiply again by a fancy 1, but this time, instead of just doing the square root of 3, I'm going to take what we call the conjugate of my denominator, which is the, instead of an addition, we're going to have a subtraction. It's going to be 1 minus the square root of 3. And I'm going to do that up top as well, 1 minus the square root of 3. Now when I do that, that actually sets me up really conveniently in my denominator, because I have 1 plus the square root of 3 times 1 minus the square root of 3, and that sets up a difference of squares. So that really just becomes 1 squared minus the square root of 3 squared. If you multiply those out by using a FOIL or a Punnett square or whatever method, you'd get the middle terms to cancel out. So that's where that would happen there. In the numerator, I'm going to distribute my 8 to my two pieces over here, and I'm going to get 8 times 1 is 8 minus 8 times the square root of 3. And so I can't multiply in there at all, but I can do that part at least. So now I can simplify this a little bit further. I can keep my numerator just as 8 minus 8 square root of 3. Can't do anything with that yet. And my denominator is going to be 1 minus. Now, the square root of 3 squared is just 3. And so that's pretty convenient, which gives me 8 minus 8 square root of 3 over negative 2. And now here's the thing. If I'm going to be able to cancel my denominator with my numerator at all, I have to make sure I can cancel it with both pieces. And in this case, negative 2 could cancel with each of these. Just be careful with your negatives. 8 divided by negative 2 is negative 4. And negative 8 square root of 3 over negative 2 is plus 4 square root 3. And let's clean that up a little bit there. Fix that so it looks a little bit better. And there you go. That's actually going to be your final answer. There's nothing further that we can do with that. That's all that it is. So this is something called the conjugate method. If we'd started with a subtraction, I just would have changed it to an addition and done that up top as well. But once again, one way to check this would be to use a calculator and just be careful with parentheses and input. But if you do 8 divided by 1 plus the square root of 3, you'll get the same decimal you'd get from negative 4 plus 4 times the square root of 3. And this is considered a simplified version of this because there's no radical in the denominator. Hope this is clear. So now we're going to do a bunch of examples. My suggestion would be that you pause the video, try it on your own, and then play it back to watch me do each one of them. It would just be a good chance for you to get some practice in. So I'm going to move through somewhat quickly because I'd like you to try them on your own and then just compare your work. Square root of 10 over the square root of 3. If you want to pause it, pause now. All right, let's see what we do. Because it's just a simple denominator, I'm going to multiply by the square root of 3 over the square root of 3. My numerator becomes the product, or the square root of that product, which is 10 times 3, which is 30. And then the square root of 3 times the square root of 3 is just the square root of 9. Square root of 30 cannot be broken down any further. If I did a factor tree, I'd only have 2, 3, and 5. There'd be no common factors there, and nothing shared. No pairs that I can break down. No perfect square factors, so that's just done. And then square root of 9 is 3, and so that's my final answer. Now, if you want to pause it before we do a 7 over the square root of 2x, you can do that now. All right, let's give it a try. You'll see that this one is really no different. It just involves a variable. I'm going to multiply by the square root of 2x over itself. Now, in this case, because the 7 originally is outside of the numerator, outside of the radical, I'm going to keep it outside. I'm going to get 7 over the square root of 2x, or 7 times the square root of 2x, excuse me, over the square root of, now I need to multiply that 2x by the 2x, that's 4x squared, which is going to equal, my 7 square root of 2x isn't going to change at all, and the square root of 4x squared can be rewritten as 2x, because the square root of 4 is 2, and the square root of x squared is x. And that's my final answer there. All right, so let's move on to the next one. A couple more. If you'd like to pause the video at this point and try out the next one, you can go for that. All right, let's see how we would do it. First thing, this is kind of like the last video. I actually would split this up so that I'm looking at the square root of 2y squared over the square root of 3. And now at this point I can actually simplify before I do anything else. The square root of 2 has to stay as the square root of 2, but the square root of y squared is just y, so I can take a y and put that in front of the radical. I get y square root of 2 over the square root of 3. Now I'm going to rationalize the denominator by multiplying by the square root of 3 over the square root of 3. In my numerator, the y is outside the radical, and the 2 and the 3 are both inside radicals, so I can multiply them and I get the square root of 6. Over, and just in the interest of space, I'm going to kind of skip the step here. Square root of 3 times the square root of 3 I know is the square root of 9, which is just 3. And once again, I can't cancel the 6 and the 3 because one's inside a radical, one's not. And it's the same thing up here. I can't cancel this 2 and this x because one's inside a radical, one's not. You can only cancel it if they're both inside radicals or if neither of them is. Alright, so there you go. There's that one. And one last example to look at. And so if you want to try this one out before you see me, go ahead and pause the video now. Alright, so then let's just give it a try. For this, we're looking to simplify first, I think is probably our best bet. And so, think about the square root of 32. It has a perfect square factor of 16. So I'm looking at the square root of 16 times the square root of 2 in my denominator, which is going to give me 5 over 4 square root 2. Now, what's convenient about that is I can actually then not have to deal with multiplying by the square root of 32, but instead just by multiplying by the radical over itself. So square root of 2 over the square root of 2. I don't need to worry about multiplying by that 4. This is going to give me 5 times the square root of 2 in my numerator. And in my denominator, it's going to be 4 times the square root of 4. Because the 2 and the 2 are both inside my radicals. And then I'm left with 5 square root of 2 over, well, the square root of 4 is 2. Multiply that by 4, I get 8. And that's my final answer. So there are 4 good examples of the basic rationalizing denominator problems. I hope it is clear. Alright, let's try the same thing with this page. You probably want to pause the video, give these a shot, and then come back and check your work. So let's look at the first one. Alright, look at my denominator, which is complicated. It has a square root and an addition. So I'm going to multiply by the conjugate over itself. In this case, because I'm starting with a subtraction, I'm going to multiply by an addition. And when I do that, I have to make sure that I distribute in my numerator. In the first case, the square root of 5 times the square root of 13. Those are both radicals, so I can multiply them. And 5 times 13 is 65. So I'm looking at the square root of 65. Plus 2 times the square root of 13. 2's outside of a radical, so it just is going to go in front like this. And then my denominator is just going to be, again, a difference of squares. So I'm looking at the square root of 5 squared minus 2 squared. Now the square root of 5 squared is just 5, and 2 squared is 4, so my denominator is 5 minus 4, which is 1. So if I have something over 1, I don't need to write that. I can actually just stick with the numerator as my final answer. Square root of 65 plus 2 square root of 13. In some ways that maybe doesn't look more simplified than what we started with, but it is. We just want to double check if 65 can be broken down at all, and it cannot. It is a perfect, it has no perfect square factors other than 1. Alright, so we're going to do the next one now. If you want to pause it and give it a shot, go for that. And let's see what we would do. I'm going to multiply by the conjugate of my denominator, which I'm starting with an addition, so I'm going to multiply by a subtraction. Negative square root of 2 minus square root of 7 over itself. And when I multiply here, I just distribute my numerator, which is going to be 12 times the square root of 2. Minus 12 times the square root of 7. All over, I've got the square root of 2 squared minus the square root of 7 squared. And when I do this, I get 12 square root of 2 minus 12 square root of 7 all over 2 minus 7, because the square root and the square root cancel out, and that gives me negative 5. Now, that's certainly one way we can keep our answer, but there is another alternative if we'd like. We can't cancel the 12s and the 5s, but if we want to cancel a negative or just move a negative up, you could rewrite this in a certain way. You could write this as negative 12 square root of 2 plus 12 square root of 7 over a positive 5. It doesn't really make a difference which one you choose here. I'd probably just keep it as the way that it was. Doesn't make too much of a difference. But either one would be fine, and that's how you do it. So I hope this makes a lot of sense, and that it's not too bad for you. And since we're posting this right around March 4th, I just want to wish you guys a happy Star Wars Day. May the 4th be with you, and enjoy your special holiday. All right, hope this works.